Welcome to this talk on a history of systems engineering, its evolution and devolution. I'm Joseph Casa.
And I'm Bruce Lerner. I'm a practitioner and researcher with a couple of patents, a BS in computer engineering and an MS in the management of engineering, and followed that up with a graduate certificate in systems. I spent 25 years contributing to and managing teams developing software-controlled electromechanical systems. And I spent some time coaching structured decision making and risk management techniques and developing tools.
And I'm Joseph Casa. I've been an international practitioner since 1970 when I first moved from England to America and became a systems engineer for a contractor supporting NASA on the Apollo program. And I've been a researcher since 1990. I'm a chartered engineer squared, which means I'm a chartered engineer in the UK and in Singapore. I'm a certified manager, or at least I was until I stopped paying the subscription this year. I have awards and letters of commendation from employers and customers, including NASA's Silver Snoopy Award for performing and directing systems engineering. I've been an academic since 1997. I have a Doctor of Science in Engineering Management and a Master of Science in Special Studies from George Washington University. I've published 11 books, and I was in the top 5 most published authors in INCOSE's regional and international symposia conferences between 1995 and 2017. I'm now an online coach and mentor living in Adelaide. So we're going to talk about aspects of the evolution and devolution of systems engineering. The first one is the introductory phase. Over to you, Bruce.
All right. As we went through this, we have put together a little legend to keep an eye on the types of information that we're looking at so that we can compare aspects of the topics. So we have one grouping of management versus technical activities. We have some things that we've tagged with specific activities associated with the system development process. We have 4 items that are associated with the systems development process itself, and one that's associated with the operations of the systems. And there are some things that we really just could not determine what they were. They were essentially buckets of items or statements about buckets of things of systems engineering. So we couldn't tell exactly one of these things to put on it. It's likely that we're wrong about some of these things and that you may have a different opinion. But overall, we're just trying to get a sense for the various aspects of the way that systems engineering has been described over the time periods that we're looking at and some of the implications about that. One of the things that's important to recognize is as systems engineering was in its introductory phase, the kinds of systems that were generating the complexity that were driving the need to have a new way of looking at the problems. They were primarily in communications initially with AT&T or the Bell systems at that point in time. So you had systems where you had banks of telephones. They went through switchboards that were controlled by people in the small sections and then to larger switchboards to get things around the country, and then back to small switchboards to get things down into the homes. And managing those kinds of systems and developing the technology to support them was one of the aspects that brought the formalization of systems engineering into play. Another large aspect that brought systems engineering to being at least the set of aspects that were initially used was World War II. And that was a system of logistics, getting materials around, building the transport systems to get those materials around, to manage those systems around the world so that we could move what was needed, to the level of having specific aircraft and artillery and those types of things that took the kinds of engineering that we're used to within the disciplines and the user interfaces to make all those things work. So those levels of complexity were the things that drove systems engineering to formalize.
And you can notice the icons on the left-hand side of the screen. And you can notice on the left-hand side of the screen the icons that we told you about earlier. The Radio Corporation of America, amongst others, recognized in the 1930s the need for a systems approach in the development of a television broadcasting service.
The RAND Corporation, created in 1946 by the U.S. Air Force, developed a useful philosophy which RAND called systems analysis.
The Bell Telephone Laboratories, Incorporated, was probably the first organization to use the term systems engineering.
If Slaughter's finding is true, the use of the term, with roughly its present meaning, began in the early 1940s. The name was new, but the functions were not.
Hall wrote, systems engineering is probably not amenable to a clear, sharp, one-sentence definition. That was 60 years ago, and as you'll realize by the end of this presentation, we can make the same statement in 2024.
Probably the first formal attempt to teach systems engineering was at MIT in 1950, and it was based on a class by G.W. Gilman, the director of systems engineering at Bell Laboratories. He used a case-driven approach and specifically an attempt to design an economical transatlantic live television broadcasting system.
The first academic training was introduced at MIT for Bell Labs by the same Mr. G.W. Gilman in December 1954.
The first textbook, Systems Engineering, An Introduction to the Design of Large-Scale Systems, written by Harry Good and Robert McCall, was published by McGraw-Hill in 1957.
So now let's move on to the second aspects, changes in the definitions of systems engineering. So in moving on to some of the many definitions of systems engineering, what I've done is I've taken the definitions and I've highlighted certain words so that the evolution and devolution can be seen. And I've also taken out some of the words that are not relevant to the point of evolution and devolution. And that's indicated by 3 dots in the sentence. And again, the icons are visible. The methodology used to manage the problem of scheduling and coordinated hundreds of contractors developing hundreds, even thousands of subsystems.
System engineering operates in the space between research and business.
The science of designing complex systems in their totality.
The application of scientific and engineering efforts to transform an operational need into a description of system performance parameters and a system configuration.
A hybrid methodology that combines policy analysis, design, and management. It aims to ensure that a complex man-made system is the one most likely to satisfy the owner's objective in the context of long-term future operational or market environments.
An iterative process of top-down synthesis.
A management methodology, 1992.
The design, production, and maintenance of trustworthy systems.
You should be seeing an evolution here. The intellectual, academic, and professional discipline, the principal concern of which is the responsibility to ensure that all requirements for a BioWare hardware software system are satisfied throughout the life of the system. Wayne Wymore, 1993, and repeated in 1994 in his book and article, Model-Based Systems Engineering.
The management function, which controls the total system development effort for the purpose of achieving an optimum balance of all system elements.
An interdisciplinary approach and means to enable the realization of successful systems. It focuses on defining customer needs and required functionality early in the development cycle, documenting requirements, then proceeding with design synthesis.
A transdisciplinary and integrative approach to enable the successful realization, use, and retirement of engineered systems using systems principles and concepts and scientific, technical, and management methods.
So you would have seen the changes in the definitions reflecting what systems engineers were doing, or at least what the systems engineers who wrote the definitions were doing. Now let's look at changes in the application of the systems approach in systems engineering. But before we talk about the systems approach, we have to start at the beginning, and that deals with general systems theory.
General systems theory was conceptualized by von Bertalanffy and published in 1950, though he had been working on this since the 1920s and published in German from the 1930s through the 1950s.
It's about developing an understanding of the social system as a whole by understanding the relationship between the systems and its adjacent system in the meta-system or context or environment.
Von Bertalanffy's model assumed a single-dimensional cause and effect relationship between the social units within the environment,
and has been modified over the years. It was later applied generally to all systems in the form of systems thinking.
Systems theory is an organizational theory that looks at the interaction between systems.
It's also a name which came into use as of 1956 to describe a level of theoretical model building.
Early research saw similarities between systems in different domains, which was the generalization for it. I've noticed that during the 1950s and 1960s, there were two types of systems being investigated and worked with. That were the natural and the engineered systems. Their principles were mostly developed independently and in parallel, and we'll see where that leads us as we head into the 70s.
And that leads us to the systems approach first documented in 1969 by Wes Churchman in his book, The Systems Approach. He was internationally known for his pioneering work in operations research, systems analysis, and ethics. The book discussed the systems approach as a way to tackle increasingly complex problems. Systems thinking as a part of the systems approach, but he did not actually define the systems approach.
In 1973, Simon Ramo described the systems approach from a more engineering perspective. The systems approach is a technique for the application of a scientific approach to complex problems. It concentrates on the analysis and design of the whole as distinct from the components or the parts. It insists upon looking at a problem in its entirety, taking into account all the facets and all the variables, and relating the social to the technological aspects. The systems approach is an application of systems theory.
In 2010, Robert Halligan defined the systems approach as an approach to problem solving that views any problem as a part of a bigger system, and in developing a solution, sees that solution being achieved through the interaction of system elements such that the properties of the whole are beyond the properties of the individual parts. And in 2023, we defined the systems approach in our talk to the British Computer Society.
The systems approach, in a systemic and systematic manner,
gains an understanding of an undesirable situation in its entirety, taking into account all the facets and all the variables by perceiving it from the appropriate meta-system depending on the nature of the problem.
Plans and performs a transition from the undesirable situation to a feasible, desirable situation via one or more iterations.
So you can see how the systems approach has evolved since 1969. We now move on to the fourth aspect, changes in the systems engineering tools.
In the 1950s and 60s, there were a number of aspects that were looked at. There was probability, single-thread systems logic, queuing theory, game theory, linear programming, group dynamics, simulation, and information theory.
Notice that all these tools are mathematical and they're used for understanding the problem by analysis and also ensuring that the proposed solution system will meet its needs. By the year 2000s, before MBSE, Steve Jenkins, in his talk at the 7th NASA ESA workshop on product data exchange, described systems engineering tools. PowerPoint, databases, which examples are DOORS, Core, and so on, word processors, spreadsheets, and drawing tools such as Visio, and so on. Do you see a difference in the tools of the systems engineer? Now we'll move on to another aspect, which are changes in the roles of the systems engineer. Arthur Hall, in his book in 1962, wrote up the traits and characteristics of a systems engineer, but didn't actually describe the roles as far as I can remember. On the other hand, William Jenkins described the roles of a systems engineer in 1969. He tries to distinguish the wood from the trees. What's it all about? Bruce?
He stimulates discussion about objectives, obtains agreement about objectives.
He communicates the finally agreed objectives to all concerned so that their cooperation can be relied upon.
He always takes an overall view of the project and sees that techniques are used sensibly.
By his overall approach, he ties together the various specializations needed for model building.
He decides carefully when an activity stops.
He asks for more work to be done in areas which are sensitive to cost.
He challenges the assumption on which the optimization is based.
He sees that the project is planned to a schedule, that priorities are decided, tasks allocated, and above all, that the project is finished on time.
He takes great pains to explain carefully what the systems project has achieved and presents a well-argued and well-documented case for implementation.
He ensures that the users of the operational system are properly briefed and well-trained.
And he makes a thorough retrospective analysis of systems performance.
I wonder how many systems engineers watching this presentation can relate to any of these activities. In 1988, Howard Eisner listed a general set of 28 tasks and activities that were normally performed within the overall context of large-scale systems engineering.
Eisner calls the range of activities specialty skills because some people spend their careers working in those specialties.
Therefore, according to Eisner, in 1988, systems engineering overlapped at least 28 engineering specialities.
Eisner in 1997 expanded his earlier list and discussed 30 tasks that form the central core of systems engineering.
The whole area of systems engineering management is covered in just one of those tasks.
Eisner states that not only must a chief systems engineer understand all 30 tasks, he or she must also understand the relationships between them, which is an enormously challenging undertaking that requires both a broad and deep commitment to this discipline as well as the supporting knowledge base.
In 1994, Brian Marr published 5 performers of systems engineering: the system specification people,
the program management people,
systems architects,
systems analysts,
and process people.
Marr noted them as being at the front end of the system development process.
And he published this in the forgotten issue of the Journal of the National Council on Systems Engineering. It was Volume 1, Number 1, July to September 1994.
There are 19 activities in the NCOSE Systems Engineering Capability Assessment Model, the CCAM, which was released in 1996. The first grouping were in the management area of planning, tracking and oversight, subcontract management, intergroup coordination, configuration management, quality management, risk management, and data management.
The second of three groups is organization, process management and improvement, competency development, technology management, and environment and tool support.
And the last grouping is systems engineering itself, which develops the system concept, definition. The third group is systems engineering itself, systems concept definition, requirements and functional analysis, system design, integrated engineering analysis, systems integration, systems verification, and systems validation.
In 1996, Sarah Sheard published her paper, 12 Systems Engineering Roles. First one was Requirements Owner.
The system designer.
System Analyst.
Validation and verification.
Logistics and Operations.
Glue.
Customer Interface.
And technical manager.
Information Manager.
Process engineer.
Coordinator.
Classified ad systems engineering.
In 2000, Sarah updated her roles, and you can see the original roles here. The name of the roles remain the same, but the activities performed in those roles have changed. And I expect that the activities performed in the roles described by each of the people describing roles are different, or rather the names may be the same, but the activities performed by those roles are different. Sarah suggested two additional roles, Systems Engineering Educator and Systems Engineering Evangelist.
The roles were revisited in an article in the 27th Annual NCOSE International Symposium, The Roles of Systems Engineers Revisited, by Hutchinson, Luna, and Wade, and they listed like this: concept creator,
Requirements Owner,
system architect,
System Integrator,
system analyst,
Detail Designer,
V&V engineer.
and notice that yellow and green highlight new roles. Systems Engineering Champion,
Process engineer,
Customer Interface,
technical manager,
Information Manager,
coordinator,
and Instructor Teacher. And we've shown the roles that are the same as Sarah Sheard's original 1996 paper with two asterisks. In 2019, a role model for systems engineering application was published. It's based on Sarah Sheard's roles, as well as information from competency models and trainers, and the additional roles are highlighted in yellow. Modeling Engineer,
system architect,
System Interface Manager,
technical manager,
Leader,
stakeholder interface manager,
Requirements Engineer,
life cycle engineer,
Implementation Engineer,
validation and verification engineer,
Security Engineer,
process owner,
Configuration Manager,
information manager.
Entrepreneur. In 2024, Sarah Sheard submitted a paper on the evolution of systems engineering roles to the 34th Annual Symposium of the NCOSE in Dublin, Ireland. They are Systems Engineering Champion,
coordinator, leader,
security engineer,
educator,
implementation engineer,
information manager,
innovator, initiator,
life cycle engineer,
system modeler,
process owner,
requirements owner,
systems architect,
system designer,
system interface owner,
stakeholder interface manager,
technical manager,
validation and verification engineer.
I notice here that there is a move towards process engineering away from direct engineering of product.
Interesting. And now we'll move on to the two systems engineering paradigms. How many of you know or realize that there are actually two systems engineering paradigms? They are the A paradigm, which starts with understanding the problem. It creates a ConOps, a design and architectures. It then creates the requirements from the ConOps, and successful projects are characterized by a common vision of the future desirable situation, and that is in the ConOps. It's the original systems engineering of the 1960s. It also creates or architects a process to realize the solution, and that ends up in the systems engineering management plan. And references to that are shown here, Beamer and Sage and Kasser and Palmer. The B paradigm began in the 1970s and was institutionalized in the V diagram in the 1990s. It was documented in the standards. And requirements are one of the inputs to the systems engineering process. And I cite the textbooks by James Martin, Howard Eisner, and Charlie Wasson, as well as DoD 5000 as sources for that statement. And the B paradigm creates the ConOps from the requirements. And I cite Densler and Mackey and Guo as sources for this statement. And the B paradigm is inherently flawed because there's no way of knowing whether the requirements are correct, complete, until the system's actually been built, by which time all the funding has been scheduled and the time has been used up. And it's still taught in most systems engineering courses today. I can describe the A and the B paradigms pictographically like so. In general, A paradigm starts with a ConOps, produces a system architecture, which then creates the requirements, a matched set of specifications actually for the system and subsystem requirements, and then that feeds the subsystem design. On the other hand, the B paradigm starts with gathering the requirements, collecting the ConOps, and then creating the system architecture, which goes into the subsystem design. And I've even seen a hybrid, which starts with a ConOps, generates the requirements, and then creates another ConOps and goes to the system architecture and subsystem design, which makes things even more complex than it needs to be. It's shown as a linear for educational purposes. For example, an infeasible requirement may modify the ConOps, which would be shown as a confusing feedback loop. There are constraints, legal, safety, and so on, that also drive the ConOps and the system architecture in both paradigms. And the system architecture may change during subsystem design. Now let's take a quick look at the early standards for systems engineering. The standards are freely available from World Wide Web, everyspec.com. There's no reason to pay anybody for them. And I suggest you take a look at them because there is a lot of useful information in those standards. The first standard we'll talk about is MIL Standard 499. It was released in July 1969. Its purpose is to develop a systems engineering management plan, not to do systems engineering. And it provided 2 templates to be tailored. But tailoring doesn't seem to have taken place. MIL Standard 499A, which came out in 1974, took the word systems out of the title and just became the standard for engineering management. Drafts of MIL Standard 499B and 499C appeared, but were not released when the government went away from standards.
EA 632 was first released in 1994 and updated in 1999. It is actually a process for engineering a system rather than specifically for systems engineering.
IEEE 1220 was first released in 1998. It's management of the systems engineering process. Again, not doing systems engineering.
ISO IEC 15288 from 2002 was about processes. Enterprise processes, there were 5 management processes out of 5 processes. Project processes, 3 of them were management out of 7 processes described. Technical processes, there were 0 management out of 11 processes. The agreement process had no management out of 2 descriptions. It was updated in 2008, 2015, and 2023. Is that evolution?
The original purchase price of the standard was 168,000 Swiss francs, which restricts dissemination. Bruce, I know if I wanted a standard widely disseminated, I would charge a nominal fee just to cover the costs. The DODAF came out in 2004. The original purpose of the DODAF is to provide communication and timely information to decision makers involved in future acquisition of communications equipment, not systems.
Volume 1 was 83 pages long with definitions, guidelines, and background.
Volume 2 had 249 pages of product descriptions.
The desk book was 256 pages long, which was supplementary information to framework users.
The core data model had 696 pages and over 1,200 data elements. The cost of implementing the DODAF in 2003 was described in this paper by Scott Davis in the NDIA Systems Engineering Conference in 2003. 45,000 man-hours to create a DODAF for his system. I don't think any comment is required on that. Now we'll move on to a historical sketch of NCOSE.
The National Council on Systems Engineering, NCOSE, was founded in 1990.
It set aside the issue of defining systems engineering to avoid polarizing the participants, according to Brian Marr.
In 1991, Fosberg and Moos introduced the V model of the V paradigm to systems engineering at the NCOSE Symposium.
It added the prefix I for international to NCOSE, but NCOSE remained a California corporation, and that was between 1995 and 1996.
In 2004, the Certified Systems Engineering Professional Certification was introduced.
In 2007, NCOSE proposed a systems engineering graduate reference curriculum in systems engineering based on the B paradigm, and it was supported by the U.S. Department of Defense's Office of the Secretary of Defense.
Also in 2007, NCOSE introduced the MBSE initiative at the NCOSE International Workshop.
But in 2009, the participants in the academic forum at the NCOSE International Symposium in Singapore rejected the graduate reference curriculum And there is a video of that academic symposium posted on YouTube. We had produced it in the IS as an experiment to see if we could actually record sessions in the symposia for publication at a later time for people who were not able to attend the symposium. I mentioned that in one of the Nkosi cafes, and somebody asked to view it, so I put it up on YouTube. And by 2024, MBSE has apparently devolved into the MBSE Michigas as being the true Nkosi systems engineering. I also found this as part of the research. Mike D presented a model-based systems engineering initiative in 2007. And there were quite a few objectives stated as part of MITA. One of them was to create an enterprise model of Nkosi. And I never heard of that model being created. And if it was, I really would like to see it. And Nkosi published this view of systems engineering in 2009. Now we'll move on to the 9 perspectives of systems engineering. When I started to teach systems engineering, I started looking for textbooks to use in my classes. And so I found a few. Some of these books I found later as well. Some of them have covers that don't have any artwork on them. But when I read through the books, I noticed that there was some commonality, but there was an awful lot of differences between them. And I try to make sense of the differences between them, somewhat in a similar way to making sense of the roles and the activities. And I was able to separate out all the activities into 9 different perspectives of systems engineering. And we published that in Rome in 2012. Those 9 perspectives are life cycle,
process,
problem,
metadiscipline,
domain,
systems thinking and non-systems thinking,
enabler,
specific system,
and model-based systems engineering, which showed up a little later. And these perspectives are expanded from and different to Brian Ma's 5 types of 1994.
So, Joe, how exactly do these different perspectives fit into the system life cycle?
Well, I'm glad you asked me that question, Bruce, because that's on the next slide. They're mapped into the system life cycle. So let's take a look at the system life cycle. And I'm using non-loaded words. Like understand the problem, define the solution, realize the solution, validate the solution, operate, dispose. Now we know that there's a manage function in there. Somebody has to manage the work that's being done. Well, system specific takes place in any of those life cycles. Following the process, those people are in the purple area, realizing the solution system and validating the solution system. The problem-solving people are at the front end, understanding the problem and defining the solution. They're also working in the maintenance and upgrading side where they're facing problems as well as disposing or recycling. The system thinking and the A paradigm people are working in the front end. The domains, well, that can be any part of the life cycle. The non-systems thinkers and the B paradigm are working in the purple area. That's the so-called systems engineering process. And MBSE in practice seems to be in defining the solution system to remedy the problem. And the enablers are working in all parts of the system lifecycle. And engineering of systems is in the system development process, realizing and validating the solution system.
Ah, interesting.
We can discuss it in the question and comment section later. And that brings us to the comments section. Before I move on to the comments, I would point out that the picture you're seeing of me is there for a purpose. It's there to point out some of the books that I read that go back to the 1950s when I was doing portions of this research at the National University of Singapore while I was a visiting professor in TDSI. So the comments we're going to make about the findings are the OV1 for the use of the DODAF itself, comments on roles and activities, the focus of the standards, the increasing degree of micromanagement in the standards, my impression of systems engineering, some questions Bruce asked during the development of this presentation, and then we'll open it up for a general discussion. The OV1 describes the use of the system. So what I'd like to do here is show you Dilbert's use of the DODAF. Here's the DODAF you asked for. I don't understand any of it. I can't tell if it's right or if it would embarrass me. I can't ask for a second opinion without looking stupid, and I can't distribute it because it might be wrong. I'll put it on this pile and hope something changes. Time passes. The secretary asks, should I shred your pile of indecision? And the boss replies, make it look like an accident. What a waste. Looking at the roles and activities. As part of the research, we separated out systems engineering the role and systems engineering the activity. And that goes back to the symposium in 2012. Systems engineering the role is what the systems engineering actually does in the workplace. That's observed. And that showed up in all the roles that you've seen earlier in the presentation. And you also saw the evolution of the roles and activities performed in those roles from 1969 to 2024. Systems engineering the activity, on the other hand, are the traditional activities associated with and based on A paradigm systems engineering, with the addition of systems integration and testing, because the A paradigm focused a lot on the front end, and most of those A paradigm systems engineers worked in the front end of the system lifecycle. And so some observations. The statement that Arthur Hall made, systems engineering is probably not amenable to a clear, sharp, one-sentence definition, still applies 60 years later. And I hope that some of the findings from this presentation have shown you why. Systems engineers perform non-CETA activities as well as CETA activities in their role. A systems engineering body of knowledge based on roles is impractical because you can see those roles cover management and all sorts of other activities. And so the body of knowledge would be extremely large. And by the time that person has attended enough courses to learn it, they would be approaching retirement age. And just because a systems engineer does an activity doesn't make it CETA. The roles have evolved to include a systems engineering champion. Why do we need a systems engineering champion? If systems engineering had delivered on its promises of the 50s and 60s A paradigm, people would be rushing to make sure that they're using systems engineering. Why do we need a systems engineering champion?
So this is a view that summarizes the icons that we had put throughout the presentation in a format that lets us take a look at how strongly are we leaning between technical and management activities, and which of the actual technical activities we're spending the most time in. And there's an outlier sort of by itself of where do we spend time, or where have people spent time thinking about how we work in operations. So if you take a look, I find that there's a pretty even split between the talking about management and technical activities in the sources that we use. There is a strong lean to the left side of the V if you take a look at the number of times we talk about analysis and design versus some level of implementation or Q&A or V&V. And management statements are mostly program project. When you talk about management, there's some IT, but there's almost no business management associated with those things. So that is a sort of a summary of how this has been discussed over the years in the publications. This view was suggested by Joe. I've consolidated the data by decade to see if there's an indication of the evolution and devolution. The details of the data show that we actually have a very small sample. The sample does, however, capture sources that were well distributed in their time frames, so were either indicative of thoughts at the time or actually just influenced the thoughts of the times. So what I see is technical and non-technical management references have remained almost evenly split with a slight tilt to non-technical. Quality assurance, or V&V, was a 90s thing, but didn't remain in focus in this century. I am surprised by the decrease in analysis references, and actually shocked by the lack of implementation references, since there appears to be, to me, so much discussion about being involved in the design of the subsystems. I expect that a more thorough investigation of sources in each decade and a more formal definition of the counting heuristics would make this view much more valuable. I'll be interested to hear your thoughts on this information.
If you look at the focus of the standards in chronological order, 499C, 632, 1220, the CMMI, and 1528, Eric Anna and Riccardo Verlerdi looked at them and published their results in 2006. And you can see that the whole front end of the A paradigm is totally missing. And some of the elements of the B paradigm are documented in the standards. So basically, those standards follow the B paradigm, and the gaps are there, I think, because the people who wrote that standard were not doing the gaps. So the people who wrote Mill Standard 499C had no experience in 3 rows. The people who wrote EIA 632 had no experience in 2 rows, and the people who wrote 1220 had no experience in a different 2 rows, and so on. If you look at the degree of micromanagement in systems engineering based on the number of pages in the documents, the very first one I could find was the Air Force Standard in 1967, had very few pages, so not much micromanagement. 499 had a few more. By the time you get to DoD 5000, you've got an awful lot of pages, which means an awful lot of micromanagement. And what do you think the number looks like in 2024? I would say, given the fact that the digital age means documents are no longer page limited due to the cost of printing, the line would be increasing vertically.
So, Joe, we've talked about this before. You've really talked about there being some right ways of doing systems engineering, and that you're interested in producing the right system delivered to the right place at the right time, providing it at the right cost with the right solution and solving the right problem, even if the problem changes during the system development process. What do you think now?
Well, you're right that that's what I thought, but I realized in the course of creating this presentation that I was wrong. The purpose of systems engineering is to create standards and guidelines. The standards and guidelines then ensure that the purpose of systems engineering is to create more work for more systems engineers by making things excessively complex and complicated, and by giving them lots of forms to fill out instead of doing something productive. You don't believe me? Check out the list at this website. Bruce, when we were preparing this presentation, you kept coming up with questions, and I kept saying, those questions are not within the scope of this research, and we'll get to them later. So would you like to remind me what those questions were?
Sure, Joe, I've been keeping a list. My first set of questions were directly driven by the roles and processes you've seen in the presentation. The second set of questions is driven by the references to the systems approach and the high management content in the slides. This second set are indicative of topics I have been pursuing for a couple of years now and receiving varying and conflicting input on. I don't have any answers yet.
I totally agree with you. And I'm just wondering which of those questions we should answer in our next presentation.
We ought to ask the group about that.
Exactly. So I'm now going to return the microphone to the session chair to moderate the questions and discussion. Thank you very much for listening.
Thank you all.